I'd like to go ahead and get started. After all, this is AGU, and things are scheduled in a manner that does not allow any flexibility or extra time, and there is another lecture that starts the exact minute that this one ends in this same room at 9 o'clock, and I want to make sure we give our speaker all of the time he deserves. So I'm Steve Kummer, the chair of the Atmospheric and Space Electricity Focus Group, and this is the 2012 Franklin Lecture. The Franklin Lecture began in 2004, and since then we have had a series of pioneers in atmospheric and space electricity research. Since it's new enough, I can actually list the past speakers. We had Phil Kreider from the University of Arizona, Don Gurnett from the University of Iowa, Martin Newman from University of Florida, and Dave Sentman from the University of Alaska. And we are pleased today to continue that tradition of pioneers in atmospheric and space electricity research with another distinguished researcher in the field, Dr. Earl Williams. Earl is currently in the Department of Civil and Environmental Engineering at MIT. Earl earned his bachelor's degree in physics from Swarthmore in 1974. After that, he moved to MIT, where apparently he liked it because he never left. He began PhD work, receiving his PhD in 1981, and then transitioning through a progression of postdoc faculty and research positions, all again at MIT. Earl's research background spans a very wide range of atmospheric physics, from the very short space and time scales of lightning and streamers to the very large spatial and time scales of climate and global spatial scales. To me, and I think many of you know this, what really stands out about Earl, as well as his distinguished research, is his unselfish cooperation in research, to quote from the AGU motto. Earl is one of those guys who is always fully engaged, always asking questions, and always giving his best ideas to everybody he's engaged with, from early stage PhD students to the most senior researchers. And by helping everyone the way he does, he plays an outsized role in advancing our field. And for that, along with his outstanding research, Earl was elected AGU Fellow in 2010. So with that, I'd like to ask that you please join me now in welcoming the 2012 Franklin Lecturer, Earl Williams.
Thanks for the very kind introduction, Steve. It's very good of you. Can everyone in the back hear? There was some question about the microphone. Okay, as Steve indicated, the talk is about lightning and climate. There are a lot of topics here. I'm going to try and cover all of these issues. First, a global perspective on thunderstorms and world views on the topic. We'll talk about convective available potential energy versus aerosols as controlling the lightning activity in the present climate. Natural variations in global temperature and lightning, there are 4 of them we'll discuss. The impact of urban areas on lightning, increases in lightning at high northern latitude, some long-standing puzzlements about the 11-year solar cycle, and still unresolved, but worth discussing. Long-period trends and stability of tropical chimneys, and we'll be looking at hydrological data for that purpose to go back further in the climate record. We'll also discuss lightning and atmospheric chemistry, speculate about lightning in a warmer world, and conclude. Let's start with the more certain aspects, because there are lots of uncertain aspects of this topic. The certain aspect is that thunderstorms are the largest form of moist convection we know about. And when you think about distributions, this represents the tail of the distribution for moist convection, and generally the greatest volatility is found in the tail of the distribution. So it's a worthwhile thing to examine from the standpoint of climate change. Thunderstorms are the deepest clouds we know about. They're giant ice factories that transport water substance from the boundary layer, where it's in very rich concentration, to the upper troposphere, where it plays an important radiative role. Thunderstorms tend to be positive dipoles. This talk is in honor of Benjamin Franklin. It's appropriate to say a few words about Ben. Ben correctly discerned that thunderstorms were of this polarity. That was an achievement in itself with the rudimentary instruments he had, but more remarkable is that he identified that there were two polarities of electricity. Imagine yourself trying to do experiments to determine how many polarities there were. If there were 3, for example, or 4, Franklin correctly discovered there were 2 polarities. Now, a couple of slides about worldviews. The majority view, and hence the majority of the material in this talk, has the arrow of causality running from weather and climate to electrification and lightning. A minority view is that electrification and lightning can influence weather and climate. Brian Tinsley is a champion of this view via cloud microphysics. Atmospheric chemistry is also in this category because lightning produces greenhouse gas substances. And forest fire initiation by lightning is also in this category because forest fires produce aerosol, which in turn feed back on the convection, as we will discuss. There are also 2 worldviews on the variability of lightning. The long-standing traditional view is that temperature and CAPE, convective available potential energy, cloud-based height, and so on, are causal variables. An alternative view is that aerosol plays a major role, and Danny Rosenfeld has been a vigorous champion of this idea for a long period of time. Now, we have these natural global frameworks which serve to motivate studies of lightning and climate, because you can get your hands on all the electrification on the planet with a single framework. We live in a thin insulator, the atmosphere, trapped between the conductive Earth and the conductive ionosphere. And that sets up the DC global circuit on the left, characterized by ionospheric potential, which is the voltage difference between the Earth and the upper atmosphere, amounting to about 250 kilovolts. And we'll be showing records of that quantity as a diagnostic for global change. You can also monitor the global lightning activity with Schumann resonances. Unfortunately, the record on Schumann resonances is much shorter than for the DC global circuit. But both of these things are valuable tools for studying climate change. Almost every meteorologist is interested in lightning, and every climatologist, but unfortunately, most meteorologists aren't interested in electricity and magnetism. If they were, we'd have more than just a handful of people interested in using these frameworks for looking at global change. Well, to study the response of lightning to climate change on long timescales, it's first valuable to understand why lightning and rainfall do what they do in the present climate. And one of the great successes of the NASA TRIM mission has been these two maps, the one at the top showing the global lightning distribution. Lightning loves continents, and there are 3 what we will refer to as tropical chimneys, the maritime continent here, the African continent here, and the South American continent, where lightning predominates with very little lightning in the intervening oceans. In contrast, the rainfall is heavy both on the continents and over the intervening oceans. And to understand this, we need to consider both thermodynamic effects and aerosol effects. A key difference is the updraft speed, which drives electrification by forming Graupel particles in the mixed phase region of thunderstorms. And there's no question that the updraft speeds are greater over continents than over oceans, but to understand why, one has to consider both thermodynamics and aerosol effects. I also point out that because we have a rainfall map here, the major drainer of the South American chimney is the Amazon River, and the major drainer of the African chimney is the Congo River, and we'll be looking at those records later on because they're very long records. Well, why should lightning follow surface air temperature in the first place? Fundamentally because of the Clausius-Clapeyron relationship, which is essentially the vapor pressure of water as a function of temperature. It's a nonlinear relationship. The slope of that relationship at 0 degrees centigrade is 7% per degree centigrade. And if there's one number for you to keep in mind during the rest of the talk, it's that sensitivity. Also because 1 degree centigrade is roughly the temperature change of the globe from 1900 to 2000, we will also be referring to sensitivities and percent change per degree or percent change per century as a useful unit to consider. The second reason that, I should also mention that this nonlinear relationship between temperature and humidity, water vapor, led Colin Price to make use of water vapor, upper tropospheric water vapor, as a successful diagnostic for global change. But the other reason that we expect lightning to follow temperature is that, at least in the present climate, CAPE increases with temperature. In a future warmer climate, it's a much more subtle issue, and we'll get to that at the end of the talk. Why is this is a illustration of CAPE, convective available potential energy. It's the area on a thermodynamic diagram bounded by the temperature sounding, the thermodynamic sounding, and the wet bulb adiabat, which is largely determined by the boundary layer properties. And this is essentially the cloud buoyancy. But we'll see later that CAPE is also influenced by aerosol and by the loading of condensate. But by itself, this is a purely thermodynamic construct. And there are many studies. I just found a couple recent ones that study the relationship between CAPE and lightning, and everyone agrees generally that CAPE and lightning are correlated. But there's sufficient scatter. You always wonder, this might be something else going on. The relationships aren't exactly one-to-one. And there are other things going on. But we now have, by virtue of a thesis study in Germany, the first global climatology of CAPE, and the results are consistent with the view that you'll have greater instability over the tropical chimney regions. South America, Africa, and the maritime continent are the maximal regions with smaller values in the intervening oceans. But the distribution of CAPE is much more diffuse than is the distribution of lightning. It's not one-to-one with the lightning. Likewise, in general circulation models, these are results from Tony Del Genio at NASA GISS. And again, we have 3 maxima in CAPE, and interestingly, a pronounced global maximum in Africa, where the lightning activity is also maximum. So this too is consistent with the thermodynamic predictions. But there's an aerosol idea here, which comes primarily from Danny Rosenfeld, and for storms that ingest continental air. Continental air is polluted. We'll show some global maps later to show this. Continental air is polluted, and when the polluted air is ingested, those are cloud condensation nuclei, and so the available condensate is shared amongst a larger number of droplets, and the droplets remain small. And if they're small, then coalescence is prevented, and the condensate gets into the mixed phase region of the cloud, where it can produce a lot of lightning. In the oceanic case, the boundary layer is clean, so the droplets are, the condensate is shared amongst a smaller number of particles, and the droplets are large, coalescence is favored, and you remove the condensate very efficiently before it can even access the mixed phase. And so you don't benefit from the latent heat of freezing, and furthermore, you suffer superadiabatic loading, and so you expect smaller updrafts over the ocean. And that's consistent with the observations, without being a thermodynamic effect. Well, this is interesting, more interesting to atmospheric electricians than others perhaps, but the very first, I think this can be credited with the very first map of global aerosol, and it was produced by the data collected on the Carnegie ship, which cruised the oceans in the 1920s. A Japanese scientist got the data and produced this map. The light areas are clean areas, and as you go progressively to darker blue, you're more polluted. And notice that the continents are surrounded by dark regions. The continents are the polluted regions on the planet for obvious reasons. It's where people live, and it's where you can make fire and oxidize material to produce aerosol. Well, we fast forward to the modern era, and these are maps produced by satellite imagery and by the composites between satellite and ground-based measurements. And again, here are 3 tropical chimney regions Green and yellow are the stronger aerosol optical depths, more pollution, and again, Africa is the winner in the pollution category, consistent with the global lightning maps. Now, there's been a debate going on about how we should calculate CAPE between land and ocean for 50, 60 years, and there are essentially two ways to calculate CAPE. The irreversible one, which is most commonly used, where you remove the condensate as the parcel rises, and the reversible CAPE, where you retain the condensate. And there were advocates in the 1980s, advocates for doing it reversibly, which essentially results in a disappearance of the CAPE, because the loading of the condensate roughly balances the thermal buoyancy. But it's now recognized, with the consideration of aerosol, that we should be using the reversible CAPE calculation for continents and the irreversible CAPE calculation for oceans. And the reversible CAPE over land gives you the latent heat of freezing, and the irreversible CAPE gives you the loading at low levels and the superadiabatic loading, which suppresses the updraft. So again, non-thermodynamic effects coming from aerosol. Okay, now we'll consider natural variations in global temperature and lightning. There are four time scales: the diurnal, the semiannual, the annual, and the El Nino Southern Oscillation time scale. I first need to discuss about one important term, which is the thunder day. And the reason thunder day is important is for long time scales, decades and a century, we need to have some measure of lightning which is stable over time. And the thunder day, I hope to convince you by the end of the talk, the thunder day observation really is a valuable thing, and we have lots of data which have not been examined worldwide. They have to be organized. The World Meteorological Organization organized thunder day data, but they didn't include any time series. They just looked at the climatology. That's valuable, but we need to look at time series for individual stations. Well, here's the diurnal time scale, and this is a cornerstone of atmospheric electricity. Brooks assembled thunder day data worldwide and showed that there were three major peaks in universal time, one associated with the maritime continent, one with Africa, and one with South America. And so the way to think about it, the sun moves across the tropics from east to west. It warms and destabilizes the maritime continent, causing an order of magnitude change in lightning. It moves over Africa and warms Africa and destabilizes it, and you get an order of magnitude increase in lightning, and so forth. And that superposition of diurnal effects leads to what is known as the Carnegie curve, which again is a cornerstone of our field. So rather modest changes in the diurnal cycle give rise to large changes in lightning activity. Well, Ralph Markson has moved this beyond a climatology by measuring ionospheric potential, this voltage difference between Earth and ionosphere, on individual days. And so he can look at the relation, and he's also looked at surface temperature data, so he can look at the relationship of ionospheric potential and temperature. And lo and behold, he gets a sensitivity, and a least squares fit here, of something close to the Clausius-Clapeyron number. Again, ionospheric potential is not entirely lightning. Lightning contributes to it, but it's also controlled by other things. But Ralph also found that the correlation was positive if he looked at the temperature in advance of when the convection occurred. If he looked at the temperature late in the afternoon, he had negative correlations, but that's the feedback effect of the convection on the boundary layer. Then we move to the semiannual variation. This is caused by the obliquity of the Earth's orbit, the 23-degree tilt. It was first shown in thunder day data that there was a semiannual signal, but there are many results involved with Schumann resonances which show it, and some of the very best observations are the results from Christian et al. Using the OTD satellite data. But the physics is simple. It's the sun crosses the equator twice a year at equinox, and when the sun is over the equator, the insolation is enhanced twice per year, and it's about a 20 watt per square meter variation. I want you to keep that number in mind too when we talk about the 11-year solar cycle. 20 watts per square meter giving rise to a temperature variation of about 3/4 of a degree, somewhat asymmetrical, but 2 peaks per year in temperature. Here's the OTD, optical transient detector satellite data. And if you look at, the nice thing about this, you can look at latitude ranges very close to the equator, month by month, and 5 degrees to 5 south to 5 north, 10 south to 10 north. The semiannual is a very consistent feature all the way up until beyond 30 degrees, and then the semiannual signal is swamped by the annual signal, and you get the traditional northern hemisphere summer maximum for the global lightning. We'll talk about that next. But one more on the semiannual. Here's the Congo River Basin, which is draining our most lightning active chimney, and the hydrological record also shows a double peak, because in the near equatorial region, people experience double rainy seasons. Twice per year, it rains heavily and produces lightning heavily. Okay, here's the annual time scale. The Earth as a whole gets hot in the northern hemisphere summer. It turns out that's when the global albedo is minimum, because the land masses are exposed to the sun, and this amounts to a 3 or 4 degree amplitude variation with a maximum in August. Well, lo and behold, the OTD lightning data also shows a maximum in August with a strong annual variation, nearly a factor of 2. But the sensitivity is about 11% change of lightning per degree centigrade globally. Just to show why we have a prominent annual variation, these are 3-month intervals: December, January, February, March, April, May, and so forth for OTD data. And you see in the lower left-hand panel the June, July, August, the northern hemisphere hot summer. You have extensions of the lightning into the deep northern hemisphere, which is very different than what you had 6 months out of phase, where the continents are narrowing with increasing latitude. So this is what is controlling the annual march of lightning activity globally. Okay, now the longest time scale, and strictly speaking, this is the only time scale I've discussed so far that's in the climate realm. Generally, time scales longer than the annual become in the climate realm. But there are 2 important concepts for the El Niño Southern Oscillation. It's the very name reminds you that it was a phenomenon studied in the Pacific Ocean. There was an oscillation in the Pacific Ocean, and the Southern Oscillation Index involves pressure differences between Tahiti and Darwin, Australia. But in reality, that's a rather provincial view of El Niño. In reality, the whole world warms and cools on the El Niño time scale, and subsidence is a very important aspect of this. And everyone in the audience who studies thunderstorms knows that you get the strongest storms when the general environment is in subsidence, when you have blue sky and you have an isolated thunderstorm forming in that condition. If you have widespread overcast and lifting, you will not have strong electrical activity. So, and the best evidence for that is that when the pre-monsoon condition is the active thunderstorm condition, and that's when you have subsidence from the upwelling in the intertropical convergence zone. And then on the second point is that in El Niño, when the convection shifts to the Pacific, it's subjecting all the chimney regions to subsidence. And that's why you tend to have greater lightning activity in the tropical continental zones on the El Niño timescale. Well, I won't cover all this. There are many studies. Many studies have been enabled by the Lightning Imaging Sensor, which is a very good sensor for studying El Niño variations. But I'll just summarize by saying that globally, the global lightning increases by about 5% per 1 degree of temperature change on the El Niño timescale. And I won't discuss this. This is the zonal variation of the enhancements, but I won't. It's too complicated to absorb in a short time, and I'll move beyond. This is from Chaudhry's work. Okay, what about urban areas? There's been a lot of recent work in this area. One of the earliest studies was by Dick Orville and colleagues, who studied the enhancement of lightning over Houston, Texas. and using many years of National Lightning Detection Network data, found a positive anomaly of lightning over the urban area of Houston, amounting to about a factor of 2. And but the question arises: how much of this is a thermodynamic effect, the result of increased, or not increased, but large concrete areas and black asphalt, which promote sensible heat and discourage latent heat transfer, and so you get stronger updrafts and stronger electrification? Or to what extent is it the oil refineries in Houston that are producing aerosol and enabling the clouds to ingest aerosol and enhance the electrification by that means? We don't know. But here's a study in Sao Paulo, Brazil, the 4th largest city in the world by population. And interesting that the Thunder Day record at the top and the temperature record at the bottom both show unmistakable increases and fairly hefty increases with time. And if you compare the Thunder Day increase with the temperature, the sensitivity is, what is it, about 10% per degree, I think. But notice that the slope of the temperature is about 3 to 4 degrees per century. That's much larger than the global warming signal. This is not a global warming effect. It's a local urban effect, probably caused by increased surfaces that can respond to sunlight and get hotter. But again, there's also a possibility of aerosol influence, but we don't have a long-term record of aerosol, so it's difficult to evaluate that. Now, in my view, the very best evidence that anthropogenic aerosol is really influencing electrification and lightning are these 2 independent results. One early one by Danny Rosenfeld and company in the United States using the NLDN data, and one in Sao Paulo, Brazil. And they both show that on weekends, when there's no question there's less aerosol because of less anthropogenic activity, the lightning activity is reduced. And notice the standard deviations. The standard deviations are small compared to the weekly variation. So it's a fairly convincing result. I know many people out in this audience don't believe that result yet, but I'm one who does. Here's another result showing that when you look at the variation of lightning activity as a function of the aerosol, there tends to be an optimal level. That if the aerosol is too small, too weak, you're like an oceanic regime, and you don't electrify strongly. And if you have too much aerosol, the droplets are so small that you don't have the formation of Graupel, which is so important for the formation of lightning. And there's a recent modeling study that corroborates this, these field pieces of evidence. Okay, one of the notable aspects of the global warming record is that this shows the northern latitudes, tropics, and southern latitudes. The northern latitudes that's where the global warming is most dramatic, particularly in the 90s. It's going up much faster than the tropics, and so we're going to focus on data from Alaska, a state which is at very high northern latitudes, and look at Thunder Day data and temperature at that location. Notice also, and I'll come back to this shortly, that the global warming is flattening. It's in the last 10 years or so, the global warming has gone away. So we'll come back to that as well. But here are Thunder Day observations in Fairbanks, Alaska, where Dave Sentman spent a lot of time. And in fact, we were working on these data when the last time I saw Dave in Fairbanks. And here is the variation of Thunder Days on the left from a period in the 1940s to present, and the temperature and the summertime temperature in Fairbanks. Clearly, both are increasing significantly. This is a statistically significant result. The Thunder Day change is almost unbelievable. There may be some urban effects here, but take my word for it. Virtually every station in Alaska, you can see significant increases in temperature. And it's unlikely that's an urban effect primarily because so many stations are doing it, and it's where we expect to see the global warming signal most prominently. I think Jim Hansen made the point once that, you know, the northern latitudes are a place where the global warming is really becoming tangible. Well, the solar cycle is a tough problem, but there are conflicting results. If you look at Brooks and Klemenova, for example, these are two studies of the thunder day behavior on the solar cycle that really confuse one. And I also wanted to mention that on the 11-year solar cycle, we're talking about a change in solar input of about 1 watt per square meter. Remember, the semiannual, we needed a lot of watts per square meter to have a 1 degree temperature change. We can't expect to have a temperature change or an important thermodynamic effect on the 11-year solar cycle. But yet there's some interesting thunder day results that there's a paper by Pinto, with a family effort, and many stations in Brazil are showing 11-year signals. And some studies in India and Southeast Asia likewise. So this definitely needs to be looked at, but I won't even speculate for reasons of time on the physical explanation of that. But I did want to show one record of Schumann resonance, and this is too complicated to absorb in 30 seconds or a minute, but this is a record over a long period of time, from 1994 to present, of the frequency of the first mode of Schumann resonance as measured in Hungary. And you see two important time scales, the 11-year time scale, which is very prominent, solar min to solar min, but then you also see the annual variations. The 11-year variation is due to ionization by solar X-rays, which change the properties of the cavity, have no influence on the lightning. But the annual variations are associated with the migration of thunderstorm activity on the seasonal time scale. So when you have a maximum frequency, you've advanced strongly into the northern hemisphere. We showed some maps of how the lightning expands into Siberia and the northern, Canada, for example. But if you go from the same time frame at solar min to the same time frame at solar min the following cycle, we see an increase. That increase has been interpreted as the advance of thunderstorm activity associated with global warming into the northern hemisphere. There's a lot of information on frequency variations in Schumann resonances. So now we're going to look at the longer period data, whatever we can scrounge up to look at long-term variations. But I wanted first to discuss the network data. You would love to be able to make use of network data to study global change, but here's the problem. If you look at the total number of lightning flashes detected by VISLA, Global 360, and the Worldwide Lightning Location Network, there are major increases with time. This is not a global warming signal. This is just because people get better and better at locating lightning with the networks, both by expanding the networks and by better algorithms for finding lightning. The VISLA thing shows the prominent annual variation I discussed earlier. Here's 3 consecutive years, but everything's increasing. The number of stations in WWLLN is increasing with time, and that improves the detection worldwide. The same thing can be seen in the National Lightning Detection network history, and Dick Orville has published a number of papers which give the annual yield of flashes, cloud-to-ground flashes from that network. It started as a fledgling East Coast network in 1983. It went to full CONUS coverage in the 1990 timeframe, and then North American coverage in 1996 or so. Maybe it's pure coincidence, but a local maximum here occurs in 1998, and that was actually the year of the highest temperature in the continental United States in 120 years. But the point is, until a network stabilizes, you can't really use it for climate change variations, and that's why we've resorted to thunder day data in many cases. But the very best record at present for looking at global lightning activity is the Lightning Imaging Sensor of NASA Marshall Space Flight Center. And that record is shown at the top for a decade. It's statistically flat. You see the northern hemisphere summer max year after year after year. This data is the global temperature from John Christie, which I received just a few days ago, and you see the same annual cycles, 10 annual cycles with northern hemisphere summer maximum. But the trend over the last decade is also flat. So we have two records that are statistically flat. The global warming is flattened relative to what it was doing in the 1990s and early 2000s. This is the same analysis, but using Jim Hansen's data, the annual temperature from his data, and again, it's flat. It's statistically flat, as is the lightning imaging sensor. Now, for longer time scales, we have ionospheric potential, but again, ionospheric potential is it's measured sporadically. There are a limited number of data. If you do least squares fits through that data from the 1960s, about 50 years of data, it's showing an upward slope, but it's not statistically significant given the great variability. Again, the lightning is in the tail of the distribution. We have a very volatile planet. You know, it goes up and down by a factor of 2 on the annual time scale. So you need to make lots of measurements to get your variance to the point where you can have some statistical meaningful behavior. This is data which was measured at Kew in London. It's air earth current, which is not the best monitor of the global circuit, but because the measurements were made in the same way year after year after year for 40 years, we decided to look at it. That data also shows an increase with time, and it's statistically significant. It's about 25% per century. Here's data from the Amazon River. There's a gauge in Manaus, which has been there for 120 years. They measure the gauge the same way every day. And the upper curve shows the annual maxima, river level, river depth, and the annual minima, and both are showing upward trends, shown on the right, over a 100-year period. Here's a record I got from a hydrologist about 20 years ago, a hydrologist in Belgium. And he said this is a very reliable record in Africa because the Congo flows over a rock ledge, and it's very stable over time. The stage-discharge relationship is very stable. And this increase in the 60s looks bogus, but it's real. I mean, there are good documentations of a tropical climate anomaly in that period. But overall, there's an increase of about 15% per century in the Congo discharge, the major drainer of the African chimney. Now, there's also a period in the global temperature record, you might call it a period of inconvenient truth, where the global temperature is stagnating or declining. It's about a 30-year period from the beginning of World War II to about 1970. And it's also clearly visible in the U.S. analysis of temperature as well. Well, it turns out that there are records by Shagnon of thunder day data for the whole United States. This analysis involves 86 stations over the United States and was published in 1985. And curiously, it shows a decline in thunder days followed by an increase just in the period of the global stagnation. Likewise, there was a publication in 2001 in Russia showing a decline in thunder day data during that period. So again, the suggestion is that the thunder day measure can be a meaningful indicator of climate change. Okay, lightning and atmospheric chemistry. I can't neglect this. Many people are working on it, and we heard results from Ken Pickering and others about the DC-3 experiment. Some general points about molecules and radiation effects. Most of what we're breathing today is nitrogen and oxygen. Those are symmetric molecules. It's the asymmetry in molecules that give rise to greenhouse effects and strong radiative effects in the infrared. And these are the bad guys. This is NOx and ozone, and they're products of lightning. And the mechanism for making bad guys out of good guys is that you dissociate these good guys into individual oxygen and nitrogens, and then they're available chemically to form asymmetrical molecules, which are radiatively important. Next slide. Better do it myself. Here's a thunderstorm. It's here's the problem. We have a situation in our atmosphere where the prominent source of NOx is not lightning, but anthropogenic effects, combustion. And so we have a boundary layer which may be filled with soil-produced NOx or anthropogenically produced NOx, and then you want to look up aloft and see what's going on there, but there's an ambiguity about how much of that comes from the lightning source, which is in mid-cloud here, intracloud lightning, and how much of it is carried up from an anthropogenic effect. But as I understand it, one of the big successes in DC3, this recent field program we heard about, is that there are big surpluses in ozone which are attributable only to the effects of lightning in the upper troposphere. And just as water is important radiatively, more important radiatively in the upper troposphere than at the surface, so is ozone. Ozone has a very strong absorption spectrum and is a very important greenhouse substance. Well, here's the most difficult part of this talk is answering the question about what we expect to see in a warmer climate. The problem with that is, first of all, Clausius-Clapeyron, if the temperature increases, then we're going to have more water substance. There's no question about that. But at the moment, we're in a flat phase of global warming. The temperature's not changing over the last 10 years. So, I can't make a strong argument about Clausius-Clapeyron for the next decade. CAPE is also very difficult to analyze, to predict, what is going to happen to the instability in the atmosphere on long time scales. If the upper atmosphere warms more strongly than the surface, you can actually have diminished CAPE on long time scales. And there are actually published results showing that there can be less lightning in a warmer climate. This is the problem of convective adjustment, and it's a very difficult one. How the whole atmosphere responds on long time scales to temperature increases. So I don't have a clear answer on that. But we did go to some GCM results. Both Dave Randall at CSU and Tony Del Genio gave me predictions for CAPE in a warmer climate, a 2 times CO2 climate. And very curiously, 2 completely independent models, this is very gratifying to me, show the same results. That is, in a warmer climate, which are shown by the green curves, you actually have a stronger tail of CAPE in the warmer climate. But at the same time, and here's the ambiguity, at the same time you have a reduction in CAPE in the region where we're normally accustomed to seeing lightning changes, CAPE values of 1 to 2,000 joules per kilogram. So, and without knowing where CAPE is actually released in waste convection in the models, it's hard to say whether this tail effect wins out over the intermediate effect. But the tail goes along with all the claims that in a warmer climate you're going to have more extreme results. There was a whole issue devoted to this topic in BAMS a few months ago: extreme weather and extreme climate. So my conclusion here is ambiguous, but one experiment we did about 10 years ago and never published it because it didn't look very exciting, but we took the lightning imaging sensor data and looked at all the thunderstorms we could get our hands on in the warm El Nino phase and the cold La Nina phase, using those 2 phases as a surrogate or a proxy for climate change, and then looked at the tail of the distribution. And there was a very, very slight tendency for higher flash rates in the warmer phase, but it wasn't exciting enough to write home about or publish a paper about. So again, that's also ambiguous. Of course, some people will say that you can't use El Nino as a surrogate for climate even, but it was our best bet. So, lightning in our future, the thermodynamic view, if the global warming were still in effect, I would say, yeah, we're likely to have more lightning in the next decade, but that's gone flat. And again, making CAPE estimates on the long time scale are difficult. CAPE is a very delicate quantity. It's a hard thing to know how it's going to behave. And likewise, the aerosol, there's much discussion about global dimming and And the fact that we may be going into a global brightening phase and then going back into a global dimming phase. So all of that is regionally dependent. So again, I'm not really willing to stick my neck out and say what role might be played by changes in the aerosol. It's just too much in a state of flux at the moment. So that's the end of the talk. Thank you very much.
So Earl has thoughtfully gone right on time, which leaves us time for definitely a few questions if there are any. Let me stand out of the light so I actually have a chance to see. Well, Earl, actually I have one for you, because there's a famous paper in the 1990s by, if I can just remember, by Williams, addressing the issue of Schumann resonance magnitude as a global tropical thermometer, which you did not mention. So what's your view on, I know that was taking, of course, a limited amount of data. What's your view on whether that is a sort of viable or reliable technique for addressing that now?
Okay, I think it is a reliable technique, but I don't put great emphasis on that work, because we took Charles Polk's data in Rhode Island to do that study. It was all hand-tabulated stuff, and it did show a very pronounced effect, sensitivity to El Nino, but it was an order of magnitude larger effect than what has been shown with the lightning imaging sensor data. So even when people cite that work, I'm somewhat uncomfortable. There's something not right about the Polk analysis. But in terms of using Schumann resonances as a good method of looking at this, definitely yes. But you have to go beyond single station data. Schumann resonances are a complicated phenomenon. Unlike the great simplicity of the DC global circuit, that involves one scalar. In Schumann resonances, you have multi-modes, and you need to use multiple stations because they're distance effects, but it will be a very important method for monitoring global lightning activity.
Any questions? Yes, Joe.
So you talked about the total amount of lightning. What about any changes in the types of lightning, or cloud to ground, or big continued currents, things like that?
Yeah, that's an interesting question. Generally, what we know from behavior in the present climate is that when the mixed phase is very deeply developed, as it is in, say, supercell storms in Oklahoma, which produce runaway intracloud lightning, the whole charge separation mechanism is elevated in the atmosphere until you'll get much more intracloud lightning relative to cloud to ground. But in a warmer scenario, then that comes back to the whole issue of, the role of the aerosol and the role of the profile of temperature, which controls the updraft profile, and so it's a tricky business.
Question, yes.
What's your view on why Africa and the Amazon basin have quite different amounts of lightning, considering the cake is qualitatively similar and aerosol sources over tropical rainforests are qualitatively similar?
Number one, if aerosol is as important as it may be, Africa definitely has more aerosol than the Amazon. You saw the map I showed of the Kinney global map, for example. But there are also results showing that Africa is more unstable, that Cape is larger over Africa. The results from Tony Del Genio show that. So I think from both the aerosol standpoint and the instability standpoint, Africa should be a winner over South America. Another way of viewing it is the Amazon is more like an ocean than is Africa. The most continental chimney, both because of elevated exposed terrain, sensible heat flux, and aerosol, Africa is the most continental of the three chimneys. The maritime continent being the most maritime, with the Amazon in between.
Any other questions for Earl? Yeah, Steve.
Say, Earl, how do you feel about these Cape calculations in the future climate in the GCMs? I think you had some values that are 6,000 to 7,000 joules per kilogram. Have you tried looking at any some of the highest capes we see often in suppressed conditions with strong inhibition.
This is a very good point. It is very true that oftentimes you'll get really high cape values and nothing ever happens. So you need to know, that's why I mentioned with the GCMs, we need to probe more deeply with the GCM to see where the convection actually is released in response to the existing cape. I've just shown the cape values, not what happens. So it may well be that those tails are unimportant for making lightning. You know, on the other hand, if something does break through, remember Darwin, we had some days when we were out front of the ITCZ and the thing would just explode. You know, there was one or two cells that just, and Hector is in that category. You know, it's sitting out there in front of the ITCZ in blue sky, and it's a very unstable situation. So, but I don't have the answer without digging more deeply into GCMs, which I'm not really eager to do.
Is there one final question? Mary Beth?
You make a lot of emphasis on the LIS data, and that's a relatively low latitude observation. Some of the biggest changes in climate are expected in the upper latitude. So I wonder if you could comment on how useful that extrapolation is.
Yeah, this is a good point also. LIS is limited in latitude, and that's why I emphasize the OTD data. And I think Hugh Christian might comment that I think when OTD was up, they were seeing Siberia brightening up for a time, you know, that they were seeing the high latitude effects. But yeah, I call that a record of global warming. It's not really true. But if you look at the distribution and latitude of lightning, I think 2 out of every 3 lightning flashes occur within plus and minus 23 degrees latitude. So you're looking at a big piece of it. But it would be better to have, it would be very nice when we have a lightning mapper and geo-orbit, obviously. Then we can see the whole show.
Okay. Let's thank Earl one last time for the 2004
Thank you very much.